Okay. Good afternoon, everyone.
Good afternoon.
All right, so what we're going to do, we're going to do something a little bit different today. We're going to look at a couple of ways of looking at probability and looking at analyzing probability in average case or expected values. So one problem that we're going to look at today is something called the birthday paradox. Birthday paradox. Everybody has a birthday. Most people have just one. You think your birthday is the most special birthday, but actually there are a lot of other people who share your birthday, which is sad but true. And the reason for that is due to what we call the pigeonhole principle. You've heard of the pigeonhole principle? Pigeonhole principle is that, you know what pigeons are? Birds. You know the ugly birds in the city, very dirty ones? The fat, you know. And they like to sleep in these holes, they call them pigeonholes. So if there's a hole and another hole and another hole, if we have 50 pigeonholes and 50 pigeons, it's possible that each of them would have their own pigeonhole. But if there are 52 pigeons, there's no way we can give each of them a pigeonhole. They have to share. So birthdays are like that. We actually, if we count the leap year, we have 366 days, excuse me. But there are, what, 7 billion people? You divide 7 billion by 366, you're going to find out that there's more pigeons, it's us, than pigeonholes. Those are the birthdays. Anyway, so the problem we're asked to solve is basically, we know that if, let's just imagine for the time being that the number of days is 365. So if I have 366 people in a room, what do we know for sure? At least one pair have the same birthday. Could there be 2 pairs? Could there be 3 pairs?
Probably.
So at least one pair. Has to, because we get the 365 pigeonholes, 366. So the question is, how many people would have to be present? I mean, if we go back to what Jamie just answered, the probability of 2 people sharing the same birthday with 366 people in a room is 100%. It's certainty. But the probability, now again, if we have 365 days, is the probability that 2 people have the same birthday with 365 people also 100%? No. It's possible that each one of those people have a unique birthday. It's possible, right? You think it's likely? I don't think so either. You think it's very unlikely or mostly unlikely? It's really unlikely. With 365 people, even with 364 people, the probability that everybody has a unique birthday is almost impossible, statistically. Not impossible, almost impossible. So our question recognizes the fact that the probability is increasing. As we approach 365, our likelihood of 2 people having the same birthday, at least 2 people having the same birthday, is increasing to 100%. 365 people. But the question is not that. The question for this problem is, what is the number of people that you would have to have with random birthdays who, so that the probability would be at least 50%. So there's a 1 out of 2 chance that they're going to have the same birthday. You see the difference in the question? So we're looking at what, and so what would you think? Well, some people might think, well, 50%, how about if we take 365, cut it right down the middle? We can't cut it right down the middle, but roughly speaking, that would be about 180. It's a lot of people. Is that when the probability is about 50%? Well, we don't know. Let's find out. Let's do some probabilistic analysis. So we're going to use something called indicator random variables. IRV, and the indicated random variable is basically a Boolean value, true or false. So X will be the indicated random variable, and it will be indexed with ij, where every person has their own index. So for example, you'd be 1, 2, 3, 4, everybody has their own index. And so for example, if you're 3 and you're 17, X 317 is 1 if you have the same birthday, it's 0 if you don't. So it's a binary variable, true, false, right? And so Xij is essentially the indicator random variable, or the event that person I and person j have the same birthday. That's the idea here. And of course, it's only a binary variable, so 1 if it's true, 0 if it's false. So another type of statistical measurement we have is expected value. Expected value. So Xij is the value of Xij, the value 1 or 0. But Exij is the expected value of Xij. Expected value is a probability. That's the probability that person I and person j have the same birthday. Okay, so we might say that probability is 1 over n, where n is what?
Number of people.
Number of days possible, because all the days, that's when your birthday can fall. We're going to make the assumption, which is not 100% strictly true, we're going to make an assumption that the probability of being born on any day of the year is the same. It's not. But we have people born on every day of the year, so we're going to just flatten it and say it's equally likely. So therefore, roughly speaking, it will be 1 over the number of possible days that you can be born in, which would be 1 over 365. So what we're going to do is we are going to do a summation, or we're going to try to add some stuff together. So what we're doing here is we're letting I go from 1 to k, where k is the number of people. And then we're going to, as I is going from 1 to k, j is going to go beyond I up to k. So for example, when I is 1, j goes from 2 to k. When I is 10, this goes from 11 to k. And so what we have is we have x sub ij. Now notice that the index I is always less than
J.
j, always less than, because j is always starting 1 higher than I. Okay. So what's the maximum value that I can be? Well, I can be k. However, when I is equal to k, what's j?
K plus 1.
And k plus 1 to k, there are no terms there at all. So therefore, the realistic maximum value here would be
K minus 1.
k minus 1, and then we would have j going from k to k, and that would be the indicator random variable x sub k minus 1k. So that would be a true or false whether the k minus first person or the second to last person and the last person have the same birthday. So actually what we're getting here is you'd say, well, why don't we just go from 1 to k and then 1 to k again? And the reason we don't go 1 to k, because, for example, suppose that person 1 and person 12 have the same birthday. Then when I is 1 and j is 12, we'd get a 1 from xij. But when I goes to 12 and j starts at 1, we'd get a 1 again. And so we would be counting 2 people, 2 pairs of people have the same birthday, but actually it's only 1 pair. We counted them as 112, and then we counted again as 12-1. So by doing this, increasing from 1 to k and I plus 1 to k, we are doing what we call combinations. So that means that any I, any j is a unique combination. We never repeat or double count anything. Okay? So the idea is basically, all we're going to do is xij in this double summation is every possible combination of 2 people from a group of 1 through k. So you can think of it this way. You match the first person to the second, third, and fourth, right? 4 people. 1 matches to 2, 3, and 4. But when you go to 2, you don't have to match to 1, 2, 3, 4, because 2, 1 already was matched with 1, 2. So when you go to 2, you start with 3, 4. When you go to 3, the only person you haven't matched it with is 4, and you're done. So 1 person is matched with 3 people, 2, 3, 4. 2 is matched with 3, 4. 3 is matched with 4. We have 6. So that's 6. And that 6 corresponds to how many groups of 2 can be pulled from a set of 4 people. And another way of writing that mathematically, who knows what I'm talking about? This is called a combination. Did we talk about combinations before this semester?
No.
So basically, the formula is something like this. We write it like this. And we read it as 4 choose 2. So if you have 4 people and you have to choose 2, how many groups do you have? So the answer for this question would be 4 factorial divided by exactly this factorial, and then divided by, again, a product here of 4 minus 2, which is another 2 factorial. Well, 4 factorial is basically 4 times 3 times 2 times 1, but 2 factorial is 2 times 1, so you only have 4 times 3 left. So you have 4 times 3,
Upon 2.
and then you still have this left, which is 2 times 1, which is 2. So this is 12 over 2, or 6. That's the 6 we got.
6.
Another question somebody could ask you, let's say you're going to celebrate a wedding. Very exciting time. In a very small private party. There are 4 couples. That means 8 people. 4 couples, 8 people. And everybody is going to have a celebratory drink. And they're going to clink the cups. Everybody has to do individually with somebody else. The question is, how many clinks will there be? Well, the number of clinks there are going to be is the number of ways that you can uniquely pair 2 people. So if I clink with Allah, that's 1 clink. We don't count Allah with me, because that's the same clink. So therefore, we would say that would be 8 choose 2. And that would be 8 factorial over 2 factorial. 8 minus
6
2
factorial.
is 6 factorial. Of course, 8 factorial over 6 factorial just leaves 8 times 7, which is 56, over 2. We have 28 clinks. It's a lot easier to do this than to actually count. Okay, there's Joe and Saad and, count all the different people. Okay, so this is a way of counting combinations. So basically what we're doing here, to go back to this, is simply summing all of the ones. So for example, tell me what is the maximum value here. What's the minimum value? 0. Excellent. Assuming that k is less than 365, of course, and we're going to assume that. But what's the maximum value? Maximum value is going to be what?
K minus 1 into K. Actually, it's a combination.
It's going to be a combination. Because all of them could be true. When would that happen? When everybody had the same birthday. Okay. So x, which is the overall number of all of the IRVs, is the summation of the xij's IRVs, individual ones. So we want, if this is x, we want the expectation of x. What do we expect x to be? We expect x to be the expected value of this double summation. And the expected value of the double summation is the summation of the expected value. So we're just moving things around, right? So now, because we know that we are doing this, we are selecting from k people 2 at a time, those are the 2 at a time, the I and the j, it really becomes nothing more than binomial coefficient, or as we call it, combinatorial coefficient. Same thing, binomial, combinatorial, same thing, of k into 2. Again, this is k factorial over 2 factorial times k minus 2 factorial times 1 over n. So what's 1 over n? 1 over n is the probability of 2 people having the same birthday, where n is 365. Okay, so as we finish this out, this k into 2 binomial coefficient becomes k factorial, k minus 2 factorial, 2 factorial times 1 over n. And we can simplify it to k times k minus 1. Because remember, this is going to be just k times k minus 1, right?
Yeah.
These two. Over 2n. So what we have is, we have k times k minus 1 must be greater than 2n. When that happens, the expectation is at least 1. So when k, okay, going back to here, so when this is equal to 1, then when we cross multiply, we get that this is equal to this. That's how we got that one. So when k times k minus 1 is greater than or equal to 2n, the expectation is at least 1.0. What does that mean? 1.0 means what? Expected value of x. That means we expect one set of people to have that. Okay, so we have a quadratic, not equation, but a quadratic inequality. So we have k squared minus k minus 2n is greater than or equal to 0. So what we want to do is we want to find out when this product is non-negative. This will occur if a k value makes it 0 or if a k value makes it positive. Those are the solutions for k. So whenever a k solution makes this left side 0, that's a solution. Whenever a k side makes it positive, that's also a solution. So we're solving for k greater than or equal to this root, greater than this is equal to this value right here. So we have our answer. We expect to have one set of people having the same birthday, and with n being 365, because that's the number of pigeonholes or possible birthdays, we expect that k is going to equal to the square root of 2 times 365 plus 1. It's approximately equal to 28. So we expect that one pair of people see the same birthday. Now this is pretty remarkable, really, if you think about it. It's pretty remarkable because we're talking about 360 possible days, 365 possible days, 356 really. But we're saying with 28 people, we already have the expectation that 2 people are going to share the same birthday. It's 28. And now how many people are in this room? Do we have 28 people?
Yeah.
3,
Roughly.
4, 5, 6. I think there are 28 people in this room.
Yourself.
I counted myself. Usually I count myself with 1.5, but this time I did a floor function, so I got myself back. No, 20, I think there are 28 people.
Yeah.
So now, so what does that mean?
One pair of people share.
That means we expect that at least one pair of people will have the same birthday. Is it a guarantee?
No.
No.
Is it more likely than not?
Yes.
Yes. Okay, so let's find out. Probability is very difficult. Now, if we cannot make this work, then I have some secondary techniques to make it work. No, it's not cheating. Okay. All right, so let's find out. Okay, so now the very difficult thing is you guys have to remember your birthdays. Everybody remember their birthdays? You can't change your mind. All right, now, even though we're from all over the world, I believe everybody uses the same months. So we're going to go January, February, March, April, May, June, July, August, September, October, November, December. All right, so all I want you to do right now is I want you to, remember, just think of the month right now. I want you to raise your hand if you were born in the month of January. Raise your hand. Unbelievable. You have twins or something? Twins, by the way, is a problem. But they're not twins. Okay. I see 2. 1, 2. Raise your hand if you're born in February. I have some bad news for you. Nobody has your birthday. That's very bad. Okay, March.
Oh God.
Yeah, you're in her camp there. Wow. Oops, we were say 3. It's 1, right?
It's 1.
Okay, April. 1, 2, 3. It's my birthday, isn't it? It's May. That's a beautiful month. Look at the happy people here. 1, 2, 3, 4, 5. 5 Mays. Okay. June also should be kind of popular. No, not this class though. 2 people. Yeah, you count. Yes. Okay. Okay. July. July birthdays. Look at how lonely that is. Single July. August. Everybody's born in December, right? Okay. September. September. Oh man, you guys gonna have a party. 1, 2, 3. October. October. You have to think about it, didn't you? It's still October. Okay. November. November. Wow. 1, 2, 3. And I guess the last one is going to be December. We have 3 people in December. Okay. Now this is kind of fascinating in a sense because if you think about it, these months right here, they have no chance. Right? But notice that the people that do have a chance, how many days in a month? About 30, right? But the most we have in any one month is 5. So you think like, that's the best chance we have if we don't get that one. All right, where are my January people? January people, okay, what's your number?
24.
So we're going to circle that, no good. April, where are my April people? 8.
9.
Who's April? There's another April.
Yourself.
I did, but there's 3. I have 3. Did I make a mistake?
Your birthday.
Oh, they. 2.
2, 9.
10.
Oh.
My son is the 8th. All right, May, your biggest chance right here. All right, May people, raise your hand again. Raise your hand. Okay. Give me the number, Jamie.
13.
11. 22. 8. 12.
11, 13.
We got it?
Yeah.
Almost.
No,
What was it? What you are?
13.
13.
11.
12.
Okay. 8, so no hit? Don't get so much joy out of this. Okay. All right, so June, where are my June people?
12.
September. September. Okay.
6.
25.
3.
October. October.
9. 7.
It's a very dramatic. Okay, November. 3 people. We have 3 people. You guys are really our last chances here. There should be 3. Who's my last? Oh yeah. Okay, go for him. 5th. Thank you, probability. I'm not joking when I say I usually get this successfully done. Get it? Now, what happened? So that was very exciting. So look at this. See, it's a good thing you came today, right? Otherwise, you could have thrown the whole thing out of balance. What's the last November?
This.
27.
So you're not a match. And then just FYI, so December people, who are my 3 December people, we don't want to forget you. Who's December? Ken's? Okay.
24th.
21st.
I mean, how cool is that? Expected value is 1. What do we get? 1. I love it when the expected value is what we get. We like to get what we expect. Probability is a very powerful thing. Now, if I didn't get any, what do you think I would do?
Figure out, cross out that.
Of course, I would be sad. Okay, but after I got over that, then I would say, okay, let's pull in some people who are not here. When is your mom's birthday? And each one of those people is like having 20, 29, 30 people, and the probability, the expected value is growing. So, and it happened one time. It was one of my favorite classes that it happened to. I was teaching, this is a number of years ago, we were talking about this problem, and we had a class, and basically we went through the whole process. We had nothing. So of course I was like, but then I remembered, outside of the classroom was my son. he was actually taking a class. He was taking a gap year between high school and college, and he was taking a class at UB in the evening, and he was sitting outside waiting for me to finish, which is a very long wait, right? So he was sitting down, but the class was almost over, and he's a little bit shy. Daniel, come here. No, I don't want to go. Daniel, here. Okay, so Daniel comes in, and I said, Daniel, tell everybody when your birthday is. And I already knew that somebody else had his birthday. So he says, September 9th. And that was that one person. That was it. That's all we needed. It was a very, we're prime zone. So it's very interesting. But anyway, so this is interesting. Probability is a very important thing. It does, now, so probability does not, again, absolutely does not mean that it's always going to work out. It means so when the probability says 75%, it means that it will work out 3 out of 4 times on average. So if you're that one class out of 4, it doesn't work out, but then 3 other classes it works out. That's probability. Averaging. It's always very, very important when you understand that. Okay, so, so that's a nice result. So let's take a look at another type of probability type algorithm. So this is another problem that we like to look at. It's called the hiring problem. There are 2 hiring problems. One is the more straightforward one, and one is a little bit more advanced, but they're both, why is this like this?
Yeah.
Oh, it's better, okay. It's me. All right, so here's what's going to happen. We're going to, again, look at the average expectancy, what's going to happen. We're going to use an employment agency to hire a new assistant. Okay? And the agency is going to send us one candidate each day. So for example, so we want to hire somebody, so let's say there are going to be 10 candidates. So in the first day, they're going to send us person 1, then person 2, person 3, 4, 5, 6, 7, 10 consecutive days. And the rules for this hiring algorithm is we're going to interview a candidate and must immediately decide whether or not to hire that person. Now, initially, we don't have anybody at all hired, so the first person will automatically be hired. We're going to take that person because they are the best than nothing. Thank you, we're going to hire you. You're better than nothing. Well, thank you. That's a high compliment. But if we hire somebody and we already have somebody working, we must immediately fire the current person. That's the bad news. Okay. So the first person we hire automatically. Now, there is a cost to this algorithm. And the cost is to interview the candidate is CI, cost of interviewing, and CH is the cost of hire. So every time since we're going to interview everybody, we'll do N times CI because all N candidates will be interviewed. But we might not hire all N of them, depend upon how good they are in terms of their ranking. So we are always going to hire somebody at all times, and we're always going to hire the best candidates seen so far. So whenever you hire somebody who's better than the current person, we have to fire the current person, and then we hire the new person. Okay? So what is the cost of this strategy? So the first thing we're going to look at is we're going to look at the pseudocode for this. And the pseudocode is we're going to assume that the best candidate has a value of n, and the worst candidate has a value of 1. So a value of 0 is worse than worst. So we're going to initialize best to 0, and then we're going to loop for all the candidates. We will interview candidate I. If this I is better than the candidate best, then best gets the value of I, and then we hire that person. So we will always hire whenever I is better than the best so far. Okay? So we're going to determine the total cost of hiring the best candidate. If n candidates exist and m are hired, then the cost of hiring and interviewing is theta nci plus mch, where m is less than or equal to n. Okay? So we have to pay nci to interview no matter how many we hire, so we focus on analyzing this part right here, mch. MCH varies with each run. Let's think about it. In the worst case of this algorithm, M is equal to N. Can you tell me what the candidates look like, the order of those candidates, so that we have to hire each one?
Ascending?
Their quality is going from worst to best. So candidate 1 has a quality of 1. Candidate 2 a quality of 2, 3, 4, all the way up to N. So whenever we see 1, well, we hire because we don't have anybody else. But 2 is better than 1, 3 is better than 2. We hire everybody. We're going to assume that the candidates are being sent to us not in this weird way, but at random. So if they're being sent at random, what's the probability that we get the worst case? Is it very likely to happen? No, because how many ways can we get them to be in order from worst to best? There's only one order for that, right? And how many different permutations or orders are there in n candidates? N factorial. So the probability of them coming in this order is 1 over n factorial. So if there are 10 of them, it's 1 over 3.6 million probability. It's not very likely. Could it happen? Yes. Same day that you're going to win the lotto. Probably, right? So it could happen, absolutely. People think that good things happen in pairs, right? Yes. Am I right? So something, they for example, they open a cookie and the cookie has some great fortune. Oh, you have to buy a lottery ticket because you're lucky today. Something good happened, so something even better has to happen. What do you think? Not so much. You believe that?
I think that's what people believe.
We all want to believe fairy tales.
Yeah. It's more likely that when something bad occurs, there's something worse will occur.
Well, people also believe that bad things happen in threes. That's a saying. Bad thing happen in threes. So if something bad happened and something else bad happened, then you're waiting for like something really horrible to happen. My dog was run over by a car. My cat was, a crane fell on him. So you want to stay away from your best friend. You'd expect something bad to happen. But anyway. All right, so if the candidates are always in this increasing order, then the cost is going to be NCI plus NCH, which is big O or theta NCH. Now that's very simple, very nice, but we're more interested in the average case. And the average case always involves some probability, some statistical way of looking at things. So we're going to use the knowledge or make assumptions about the distribution of inputs, meaning the quality of the candidates, to determine the average case. The expected cost is based on this distribution. We can assume the candidates come in random order, and so we will, once we randomize the candidates, their ranks are 1 to n. So now after we randomize them, we could get rank 15, rank 1, rank 7, right? So the ranks are going to be crazy all over the place. So the ordered list is rank 1, rank 2, rank 3 is a permutation of the numbers 1 through n. So rank 1 is whatever is the rank of person who comes first. It could be 1, could be 2, could be 3, could be n. So anybody could be anything. So some permutation. So the links, the list of ranks is equally likely to be any one of the n factorial permutations. The ranks form a uniform random permutation. Uniform means equally likely. Random means that we don't have any pre-selection, and permutation means order. So we want to determine the number of candidates who will be hired on average, assuming that the permutation of the ranks is uniformly distributed. Again, we're trying to make some simple assumptions. Probabilistic analysis can be used when the distribution is not known or cannot be modeled computationally. We can impose a distribution on the inputs by using randomization of the algorithm. All we're doing here is we're basically saying, okay, this is just a pseudocode to randomize the people. So if you don't believe that the candidates are going to be randomized by the agency, and you want this solution to be true to your actual results, which you can say, okay, you're going to send us 15 candidates. Please send us all the 15 names. We randomize them, and we invite this person. So we can, this basically makes sure that whatever you get is going to be a random representation of the candidates and not a ranked or any kind of biased, anything like that. Okay, so that's all we're doing, is basically doing that kind of thing. So, so at this point, we can choose from all the candidates to interview at random. So that's fine. Instead of relying on random order from the agency, we make the random order ourselves by using randomizing. Okay, so what we're going to do is we're going to hire the person using an analysis using the indicator random variables, IRVs. And again, IRVs only have a value of 1 or 0. Okay, so that's a nice thing. And so what we're going to do is we're going to use this model. I sub A, this is the independent random variable of A, where A is an event. Event is something that happens or doesn't happen. So it's an event. So basically, 0 is the value of IRV of A. If A does not occur, it's 1 if the event occurs. So X sub A will be equal to essentially the IRV of A. So these are the X values, right? These are all the X's. So X sub A is going to be the total of the values of X for the event A, which is going to be equivalent to the IRV of A. Therefore, the expected value of X sub A will be the probability of A, the probability of A occurring. So the expected value of X sub A will be the expected value of the IRV of A. So that's going to equal to 1 times the probability of A plus 0 times the probability of not A, but that's just a 0 term. So therefore, that's just going to be the probability of A. So the expected value of X sub A is the probability of A. That's it. So xi is equal to the IRV for I if candidate sub I is hired. So X sub I will be 1 if we hire person I, 0 if we do not hire person I. So therefore, the X's are going to be nothing more than the sum of all the X IRVs. So X1 plus X2, so these are all 0 1s. This is a 1 if we hire person 1. That's always going to be 1. But this might not be 1. If we don't hire this person, it'll be a 0. And now, let me ask you a question. Is it harder to get hired when you're at the end, or is it harder to get hired if you're in the middle? At the end. Because in order to be hired at the end, who do you have to be?
Best.
You have to be the best. Because if you're not the best, that means the best came before you, the best is hired, we're not going to hire you. So given n people, what's the probability that the nth person, last person gets hired?
1 over n.
1 over n. Again, because they're at random, the best person out of n people, what's the probability they're going to be at the end? Each position, 1 over n to here, 1 over n here, 1 over n here, 1 over n everywhere, actually. Okay, so our x's are nothing more than the summation of the IRV x's. So now we need to compute the probability that candidate I is hired. So you already told me, what's the probability of person 1 being hired? 100%. But how about the probability of person 2? Well, person 2 will get hired if they're better than person 1. And person 3 will get hired if they're better than person 1 and 2. And person J will get hired if they're better than persons 1 through J minus 1. Get the idea? Now what's the probability that person 2 is better than person 1?
1 over 2.
1 over 2. What's the probability that person 7 is better than persons 1 through 6?
1 over 6.
1 over 7. So the probability is actually decreasing. 1 over 1 for the first person, 1 over 2, 1 over 3, 1 over 4. So the probability is decreasing, isn't it? What type of sequence is it that we're modeling? 1 over 1, 1 over 2, 1 over 3, 1 over 4. It's a decreasing sequence, but it has a name. Harmonic sequence. It's a harmonic sequence. Very good. Okay. Now geometric because there's no ratio, but it is decreasing. Okay. So we need to compute PR that candidate I is hired. So you can see here, and this is what it's showing, the probability that candidate I is hired is 1 over I. So for the 7th person, it's 1 over 7, because you have to be the best of the 7 to get hired. If you're not, then you're not getting hired, because somebody better than you was in front of you. Okay, so 1 over I is the PR of probability of person I getting hired. Okay, this is an example. Probability of candidate 8 being best so far is 1 over 8. Since the candidate must be the best of the first 8 candidates. Okay, so what we need to do is we need to compute expected value of x. And the expected value, remember what x is? X is the summation of all the xi's, all the 0, 1s. So expected value of x is the expected value of the summation of all the xi's. So we're going to go from 1 to n xi's, which is going to be equal to, the summation can come out, the summation of the expected value of xi. But we know that xi is 1 over I. So therefore, we already know how to solve this using the integral. This sequence is increasing or decreasing?
Decreasing.
It's decreasing. So if it's decreasing, then our continuous integral has to be back to the left. Because if we start at the same point, it's going to decrease before this one has a chance to finish 1 unit. So I have to back it up. So what we're going to do is we want to solve this. So what we're going to do is we cannot solve this because the integral cannot start from 0. Why not? Because 1 over 0 is undefined. So we're going to say this is the same as 1 plus 1 over I from 2 to n by pulling out the term when I is equal to 1. 1 over 1 is 1. Get it? So therefore, this will equal to 1 plus the integral from 1 to n of 1 over x dx. So this is the upper bound. This is the summation. We're only solving this. We're going to add a 1 later because it's just, we took it out. So this is the upper bound. We back up the index to 1 to n, and that's going to be equal to natural log of n minus natural log of 1, but that's 0, so it's just going to be natural log of n. So that means the summation from 1 to n, 1 over I is going to be natural log of n plus O or theta of 1. And so what does it tell us? It tells us that the number of candidates that we're going to hire is going to be roughly natural log of the number of candidates plus 1. Okay? So let's do an example. So if I had to, for example, hire, let's say I had 20 candidates were being sent in, right? 20 candidates. So the question is, how many would I expect to hire? Oops, if I can get my phone to work. So let's take 20. Natural log of 20 is just about 3. So basically, if 20 people are going to get hired, sent to us, how many are we going to hire? 4. So that's a kind of interesting result, isn't it? So if they give you 20 people, and you use this algorithmic approach, you will, on average, hire 4 people.
4.
The first, and then 3 more people. Now, secondary question. Are you going to hire the best in the end?
Yes.
Almost always or always?
Always.
Always. Because that's the way the algorithm works. So you're going to hire 4 people, and you will end up with the best person. How many people do you have to fire?
3.
3 people have to be fired. So, okay. So basically, using this, let's call it lnn plus 1, we can say our complexity is going to be theta of L is going to be theta of n times Ci plus ln n times Ch, cost of hiring.
Come again.
Right? Any questions? Is that easy or hard?
Come again.
Easy or hard? Pretty easy, right? Straightforward? Okay, you think about it a little bit more. So now we're going to make the problem just a little bit more interesting. We're going to change the problem up. We're still going to try to hire an assistant. But instead of having them come in at all, we're going to do something called online hiring. Online hiring. So what we want to do is See, the problem with this last solution is we will end up with the best person, for sure, but we have to interview everyone. So 20 interviews. Each interview is 1 hour of time. So that's 20 hours. Hiring, it's a process. So it's going to take, the HR is going to take them time to do this. Firing is a sad process. You have to fire somebody. Hey, you just hired me yesterday. I know, but somebody better came up. So what we're going to do is we're going to try a balancing act. What we want to do is we want to hire the best person, but we will settle for a person who's very good, close to the best. We'd like the best, but we'll settle for somebody who's very good. We want to, in fact, what we want is we want to maximize the goodness of the person we hire in a way that can't be guaranteed because we're actually not going to even interview everybody. People are still going to be coming in at random, or we're going to have access to people at random, but we're not going to interview everybody. Well, if you don't interview everybody, and the people are coming at random, there's a chance you won't interview the best person. If you don't interview the best person, you're not going to hire the best person. But our goal is not to hire the best person. Our goal is to try to hire as good a person as we can while minimizing our costs of interviewing as low as possible. So we want to interview as few people and hire as few people. In fact, we're only going to hire one time. So our cost of hiring is going to be 1 times CH. And what we want is we want the minimum CI cost of interviewing, and a maximum quality of hiring. So you can see the problem is a little bit more complicated. So the idea is this. We will not interview all the candidates. We will settle for a candidate close to the best. We want the best, but we'll settle close to the best, because sometimes the best is not going to be possible based upon our algorithm. We will hire 1 time. After the interview, we will hire the applicant immediately or tell them they will not be hired. So when you come in to be interviewed, you're going to be interviewed, and then they're going to tell you, we're not going to hire you. Or they're going to say, you're hired, and then that's it. Nobody else is going to get interviewed after you. Once they hire, they're done. So we will tell immediately. So the problem is to minimize the candidates, the number of candidates interviewed, and maximize the quality of the candidate that we interview. So here's what we're going to do. We are going to interview a set of candidates in the beginning. So for example, we're going to say there are 20 candidates, 30 candidates, 40 candidates, I don't know. We're going to say, we're going to interview 7 candidates. Hello, what's your name? Okay, nice to meet you. Blah, 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 blah. Okay, thank you very much for coming in. We're not going to hire you. Second person comes in, hi, very nice to meet you. Okay, I see you have a degree from Yale University. We're not going to hire you, but thanks for coming in. Okay, so our number of people we're going to interview is going to be some number, K, J, whatever you want to call it. We're going to come up with this magical number. We're not going to tell the people that we have this magical number, but those first K people that come to get interviewed, none of them are going to get hired. None of them. No matter how amazing they are, not going to get hired. But then, after those K people get interviewed, we will have all their ranks. 12, 15, 18, 20. And then we're going to interview the following person. The first person we interview who's got better qualifications than the maximum in that initial set is hired, and we're done. So, of course, let's think about what that means. If we only look at one person in the initial group, and then hire the next person better than them, is that a good idea to maximize the quality that we hire? Do you understand that the first person has a 50-50 chance of being in the top half and the bottom half? So 50% of the time we would be hiring somebody who is better than somebody in the lower half. That's not good. And 50% of the time we'd be hiring somebody who's better than the second half, but they could be in the bottom of the second half too. You don't know where they're coming from. So interviewing one person is not very good. How about interviewing 2 people? Well, the probability that they're both bad is lower. I'm just using, If we interview 3 or 4 or 5 people, and they're coming at random, we have a better chance of having the people be a pretty good representation of the distribution of the qualities. But if we have only 8 people to hire, does it make sense to interview 5 people and never hire them? It's too much, right? Because now, 5 out of 8, which is 63% chance that we interviewed the best person, we have only a 37% chance of hiring the best person at all. Because we might have eaten them up in that group of initial interviews. So we want the initial group to be small enough, but not too small. Big enough, but not too big. I mean, think about it. Go to the ridiculous extreme. If we interview one person, it gives us no information. We'll hire anybody virtually. But if we interview n-1 people, then there's an n-1 over n probability that we've already got the best person in there. We're not going to hire them at all. And what happens if the worst person is out there? Well, we have to hire them, because we only can hire once. So if we interview n-1, and the worst person is waiting here, we're hiring them. In fact, we're hiring everybody. If we interview n-1, we're just hiring the nth person. That's not a good technique, so that's too big. It's too small. Where is that sweet spot? Where's that nice location? So that's what this problem is about. Okay, so after interviewing each candidate I, we give them a unique score. After seeing J applicants, we know the score of applicants 1 through J. So J is going to be our number of people we interview but do not hire to get an idea of the quality of the whole set. We have scores from 1 to J. We do not have scores from J plus 1 to N. Those are the latter people. Okay, so the strategy is we're going to choose K less than N, where we interview the first K applicants but don't hire them. We keep their score, then we hire the first applicants bigger than score max, where score max is the maximum of the first K quality. If score max was the highest overall score, we have to hire applicant N. Okay, so this is looking at the algorithm. So we initialize the best score as some very low number, negative infinity, for example. For I equal 1 to K, we're going to look at the best score. So we're going to look at the first K people. So just finding out what it is. So if score I is better than best score, then best score is equal to score. So we will come out with the best score. Now we're going to go to people K plus 1 to N. This is the next group. If any one of their scores is better than best scores, we return, that's a higher, and we're done. Okay, so now let's look at our events. So the events, oops. I don't know why it's like this. All right, can't do anything to make it larger and nicer. All right, so MJ will be the max over all of the scores from 1 to J. Now listen carefully. S is an event. S is an event we succeed in choosing or hiring the best candidate. S. So S is good. Okay, S is good. S sub I is an event we succeed hiring the best applicant when the best applicant is candidate I. So S is choosing or hiring the best candidate, and SI is hiring the best candidate when the best candidate is candidate I. Given. This is called a conditional probability. So the probability of S, the probability of hiring the best person, is the probability of SI over all people. Meaning, the probability of hiring the best person is the probability of hiring the first person when the first person is the best, plus the probability of hiring the second person when the second person is the best, plus the probability of hiring the third person when the third person is the best, plus the probability of everybody when that person is the best. So probability of S is the summation of these probabilities. Now, notice that from 1 to n, probability of S sub I is equal to K plus 1 to n of probability sub I. Why?
Because we are getting
Because
the best
nobody from 1 to K is getting hired. So the probability of hiring the best is equal to the probability of hiring the best ith person when the ith person is K plus 1 through n, because the first K people not getting hired. So the probability of SI, the probability of success of hiring the person when the best person is the ith person, requires two things to happen. The first person is BI, event. So in order for SI to happen, we must have an event BI, which means the best candidate is in the ith position. And the second thing that must happen is another event happens, OI, and that is that none of the candidates are hired before them. Okay, so when the best candidate is the ith one, that's the BI event. And then the algorithm will not select applicants from k plus 1 through I minus 1. That's the only way we're going to get I. If we skip these people, k plus 1 through I minus 1. So that none of the candidates in position J are chosen, where J is from k plus 1 to just before the best. So in order for SI to happen, BI and OI have to happen. Those two things are required for SI. So events BI, best being I, and O being I, meaning that we don't choose any of the previous k plus 1 to I minus 1, will make our analysis easier. So the probability that we hire the ith person when the ith person is the best is the probability that the best person is I, intersected with the fact that we don't hire any of the people before person I, which is equal to probability of BI, which is the best is I, times the probability of OI, that is, we don't hire before I. Now, this is called, what kind of probability is this? Probability of B intersect O. Probability of these two events, huh?
Separate, not occurring together.
Okay, so this is the probability of both of those events occurring together, the probability that both they happen together, happening together, intersect. So therefore, now the question is, are these dependent or independent events? The probability, they are independent events, and because they're independent events, the probability of the intersection of two events is equal to the product of the probabilities of the independent events. Independent events are very important, because if there's a probability for this event and a probability for this event, but they have an overlap, then the total probability is this, not this. It's less. If the events have some overlap, then their total probability is less. If they have no overlap, then their probability is here and here. So when they overlap, when this event happens, this event may also be happening. Because once we go here in this area, then it also happens to be this event. So that's called overlapping events. Independent events are like this. This happens, nope. This has to have its own chance. So independent events we can use as a product rule. So we have the probability of being the best at I and probability of not hiring before I are independent events. Now, probability of BI is 1 over n. The probability that the best person is in position I is 1 over n. It's equally likely anywhere. So that's the probability here. For OI, the probability that we don't hire before I, that means that the candidates from 1 to I minus 1 must be occurring in positions 1 through k. So in order for us not to hire before person I, then the best scores in candidates 1 through I minus 1 must be in position 1 through k. Why? Because if the best score is 1 through k, then it's not here before I, and we don't hire them. But if the best score from 1 to I minus 1 occurs out here, then we'll hire them before we get to I. Okay? So in order for us not to choose the person after k, which is k plus 1 to I minus 1, the best score in the entire set has to be here. Because if it's here, we're going to hire before we get to I. Okay, so in order for that to happen, the best score from I to I minus 1 must happen in that little early group. And it's equally likely in its positions. So what's the probability that the best person is in position 1 through k? That's just nothing more than k over I minus 1. Let's think about the numbers here. Suppose that my little interview group is 5. And my best person is at position 11. Let's do it differently. 5 and this best person is at 12. So I want to make sure that the best person is in the group of 5, not in the group of 11. The probability of that is going to be 5 over 11. And that's what we have here. So we have 5 over 11, because the best person at I is 12. Okay? So probability of BI, simple. Probability of OI, not too bad. And their product probabilities are this times this. So it's 1 over n times this. So it's going to be k over n times I minus 1. So now we have the probability of hiring the best person when the best person is person I. We have to now sum that over all I positions from k plus 1 to n. And there it is. So probability of S is the probability of SI, which is k over n times I minus 1 from k plus 1 to n. Now as we do our summation, of course, we can take k over n out because they're not a function of I, so they come out. So what we have is the summation k over n times the summation of 1 over I minus 1. And notice what I did here. Because this is I minus 1, what I did was I increased this to k, not k plus 1, so then I was able to increase this one here. So I decrease plus 1, and then I increase that one. Does that make sense? So I make the sum. Now notice, what kind of a summation is this right here, guys? It's a harmonic series again. Haha, okay. So this is a harmonic series. We can use our integral. So basically, probability of S is going to be k over n times this integral. Now we know the sequence is decreasing. We know the lower limit is k. Since it's decreasing, we have to go to k minus 1 because it's decreasing, so we have to back up so that we decrease down to the discrete one. And so it's going to be the upper bound is going to be integral. Notice k over n just comes out. And this is substitution because we're doing an upper bound. Integral from k minus 1 to n minus 1 of 1 over x dx. And that, of course, is natural log of x at n minus 1 minus at k minus 1. So that is our value. So k over n times natural log of n minus 1 minus natural log of k minus 1. That's our solution. Now what we're going to do is we have a value. We have a very good expression for the probability of S. But the probability of S looks like it's basically a function, right? So what do we want to find in this function? We want to find what kind of point on this function? Any point? Lowest point? Highest point? What kind of function is it? Function is probability of choosing the best person. So what do I want? I want the probability to be the highest. So I'm looking for a max. So this function is going to go like this. It's going to increase, if you graph it, and then it's going to decrease. What do we want?
Max.
We want to find out where the tangent is horizontal. Because where a tangent is horizontal is going to be a max point. To do that, we have to take the derivative of our function, which is also known as the equation of the tangent line to the function, and set it equal to 0. Because when the tangent line has a slope of 0, it is a horizontal tangent. It will be typically a max location on the function. So here is our function. So that's our function right here. So we'll take the derivative with respect to k. K is our variable of this function. So k over n times the difference of the logs. K over n times the difference of the logs. We'll take the derivative of that with respect to k. And I'm not going to go through this. It's not important that you understand how to do it. If you're not following it, that's okay. It's just a derivative. You know how to do derivatives of polynomial functions. Is this a polynomial function? First of all, let's see. How would we do this function? What is the derivative of natural log? Anybody know?
E raised to x.
You know what it is.
E raised to x.
Sure. Okay, so derive this. So we're going to get 1 over n times natural log of n minus natural log of k minus 1. It's going to be 1 over this, simplified. When we set it equal to 0, the derivative, we will find the optimal value. And when we set it equal to 0, we're going to solve for k. We find out that k is equal to n over e. So let's do this problem and figure this out, what that means. So in our particular problem, if we have, so let's go back again. Let's suppose that we have n is equal to 20, which is what we had before. So if we have 20, we'll take 20 and divide it by e. What's e equal to?
2.7.
2.71828. Roughly speaking, we get about 7.3. That's the value of k. So k says if you have 20 people at random, interview 7, and hire the first person better than the max in that group. Okay? How about if you have a person sent every week? You have 52 people. So that's 52 divided by
E.
E.
19.
We got about 19 people. Okay. Now, so let's take a look. So look at this. So this is our function. This is our function right here. Let's graph this function. So this is our k is n over e. This just shows you the values. Suppose we have 20 applicants, then we have k equals 20 over e is about 7, is what we talked about. We will succeed hiring the best qualified candidate with a probability of at least, and this is the probability. So now I basically plugged my value of k as n over e. You understand what I did? So I used k is n over e, and I got a value of 0.368. What does that mean? It means that if I have 20 people, and I use my control group k to be 7, I have about a 37% chance of hiring the best person. And that also happens to be the best chance I have, because if you look at the function, this is what the function looks like. This is our probability function. So look at this one. So the first one, so this is graphed with n equal to 20. So if n equal to 20. Notice that if k is equal to 20, we have 0% of hiring the best. Why? Because there's nobody to hire. How about if we hire 19 people? What's the probability of hiring the best? What is that probability? 5%. That's also known as 1 over 20. So the probability of hiring the best is that the best person is at the tail end, the last person. Not very good. But the function, you can see, it's increasing. And right around the values of 7 and 8 is where the values of probability of hiring the best person is maximized. If we go too far, we're going to lose, because we may eat up that person in the control group. If we go not far enough away, we probably don't have enough representation, and the best person could be towards the end, but we'll hire earlier because there's so many other people who are better than this small group. So this gives us the best trade-off balance. Okay? So just a little work. I wanted to spend a little bit of time in looking at probabilities and how you can plan on. You know, of course, all of these are problems, but they're also algorithms. They're also approaches. So you can have algorithms that do the same type of thing, give you approximations and values, and look at you're trying to optimize them. All right. So any questions? I guess not. All right. I will see you on Wednesday.